Assalamu alaikum. I welcome you to the 20th lecture for the series of lectures on advanced computer architecture. Today, our focus will be the exploitation of instruction level parallelism by using static scheduling techniques. After a brief review of what we discussed in the last 8 lectures, we will study the basic compiler techniques, loop unrolling, and static prediction techniques to understand the concepts of static scheduling. Our discussion in the last 8 lectures have been focused onto the exploitation of instruction level parallelism by using hardware-based techniques. These techniques are known as the dynamic scheduling techniques. While talking about the instruction level parallelism, we said that instructions in a basic block are considered to be the state line codes without any branches at the input and output stages, and we discussed how we can execute these instructions in parallel by using a pipelined data path. Here we noticed that the performance of a pipeline data path is limited by different types of hazards, such as the structural hazard, the data hazards, and the control hazards. These hazards are removed by introducing stalls, whereas we also noticed that the stalls degrade the performance of a system and performance of the processor while executing the instructions for enhancement of the performance. Therefore, then we discussed the out-of-order execution of the instructions to reduce the number of stalls, and this we achieved by using different scheduling techniques. The number of stalls to overcome hazards in a pipeline data path are reduced or eliminated by introducing either additional hardware and then performing the runtime scheduling of the instructions. This runtime scheduling is referred to as the dynamic scheduling. Here in our earlier discussion, we have discussed different techniques to reduce the number of stalls while overcoming hazards of different types. These techniques, which we have already discussed in detail, are summarized here in this table. Over here you can see that the basic technique used is the forwarding and bypass, and this technique is used to minimize the potential data hazard stalls. Here basically the data which depends on some earlier instruction is obtained from the internal pipeline registers, and it is made available to the execution unit instead of obtaining this data from the actual destination register. The second technique which we talked about was dealing with control hazards, and this technique is known as either the delayed branching or branch scheduling. The delayed branching is used to reduce or eliminate the control hazard stalls. Then we considered some hardware techniques for reducing the control hazards. For this purpose, we discussed some modifications in the hardware to take care of the data hazard stalls in case of true dependency. And then we further discussed the dynamic scheduling techniques by using renaming. This renaming technique is implemented by using the structure proposed by Tomasello. This technique is used to reduce or eliminate the stalls from data hazards, from anti-dependencies, or for output dependencies. Then we discussed the dynamic branch prediction techniques. These techniques are used to reduce or eliminate the control hazards. Here, the hardware predicts the behavior of a branch to be taken or not taken depending upon the previous history of operation of the different instructions. While talking about the dynamic branch prediction, we also discussed the speculation technique, where speculation technique is one when the hardware speculates considering the previous branch history that whether the branch will be taken or not taken. This technique has been found to be very useful to reduce the data dependencies as well as the control hazard stalls. Furthermore, we used the Tomasello's structure in conjunction with the branch prediction hardware to deal with the multiple issue instructions, which is an ideal case to reduce the number of clock cycles per instructions below 1. We also discussed that the multiple instruction issue processors are designated as the high performance processor. These processors are available in different flavors, such as the superscalar processors, very long instruction word processors, and vector processors. In the previous lectures, we discussed in details the static scheduling as well as the dynamic scheduling in superscalars, whereas we said that the very long instruction word processors perform scheduling by using compiler-based techniques, or say the static scheduling techniques. So far, we have not said anything about the vector processors. Today, we will start with our discussion onto the exploitation of instruction level parallelism by using compiler-based techniques or by using static scheduling techniques, whereas I will take up the vector processors at a later stage. The major static scheduling techniques which will remain in discussion either in today's lecture as well as in a few of the following lectures are summarized here in this table. Here you can see that we will be talking about the basic compiler scheduling technique, which is usually used to take care of data hazard stalls. Then we will be talking about another very useful method known as the loop unrolling. This technique is used to reduce the control hazard stalls, and then the compiler dependence static scheduling techniques will be discussed. These techniques are used for ideal CPI, that is the clock cycles per instruction, either to be equal to 1 or to reduce it further below 1 for enhancing the performance of the system, and at the same time taking care of the data hazard stalls. Then we will be also considering the trace scheduling, which is also used to achieve ideal clock cycle per instructions and data hazard stalls. And then towards the end of a series of lectures on static scheduling, we will be discussing compiler speculation techniques. These techniques are also used to achieve ideal CPI and also reduce data as well as control stalls. In order to exploit the instruction level parallelism, we have to keep a pipeline full by a sequence of unrelated instructions. From unrelated instructions, we mean that the instructions should be such that these instructions may be overlapped in the pipeline. This shows that dependent instruction in a sequence must be separated from the source instruction by a distance equal to the latency of that instruction. For example, floating point ALU operation, that is using the result of an earlier floating point ALU operation, must be kept 3 cycles away from the earlier instruction. And a floating point operation that is using the result of an earlier double word operation must be kept 1 cycle away from it. For our further discussion, we will be assuming the following average latencies of the functional units for our basic pipeline structure. These latencies are given here in this table. As you can see, the integer ALU and floating point load latencies to floating point store are equal to 0. The floating point load latency to floating point store is equal to 0 because the result of the load can be bypassed or forwarded without stalling to store. Similarly, the integer load latency is equal to 1, whereas the floating point operation latency to floating point store is equal to 2. With this much introduction to the latencies of some earlier instruction vis-a-vis some next instruction, we can discuss what is the basic of static scheduling. So this shows that a compiler, while performing scheduling to exploit instruction level parallelism, must take into account the latencies of the functional units in the pipeline. Now let us discuss the scheduling with the help of our earlier example, where we discussed the addition of a scalar to a vector, and we will see how a compiler can enhance parallelism by scheduling. Let us consider the example of a loop where a scalar is to be added for 1000 times to a vector. Now, the implementation of this particular problem in the assembly of MIPS processor where we are assuming a 5-stage pipeline architecture is shown over here. Here you can see that the data dependency in the add and store operations, they lead to the data hazard, and the control hazard is existing due to the branch not equal instruction. Let us assume that the loop is implemented using the standard 5-stage architecture with branch delay of 1 clock cycle. The functional units are assumed to be fully pipelined, and the functional units have latencies as we have already discussed, and they are now repeated in this table. Here from this table you can see that the latency is shown over here for the instructions producing results and the instructions which are using the results. The latencies are 3 when the instruction producing the result is floating point ALU operation, and the instruction which is using the result is also another floating point ALU operation. Similarly, the latency is equal to 2 for floating point ALU operation, which is another instruction which is using its result is store double word. The other latencies are also shown over here in this table. Using the latencies just discussed, let us see how the single iteration of our example program for the execution of a loop can be executed without scheduling. The execution of the code and the introduction of stalls after different instructions is shown over here. You can see that the first stall introduced over here after the first load instruction is just to take care of the latency of the load instruction, which is to provide the results to the next instruction, which is add. Whereas the add instruction has got a latency of 2 for the following store instruction. This is why after the add instruction we have introduced 2 stalls. This way you can see that one iteration, when it is executed without scheduling, it requires 10 clock cycles, which is in fact introducing a very big overhead onto the execution of the program. Let us have a look onto the program which has been scheduled by the compiler. Here you can see that the compiler had to determine that it could swap the add instruction and the store instruction by changing the destination address of the store instruction. Similarly, you can see that the address 0R1, that is the address for the first load instruction where from the data is to be obtained, is replaced with 8R1, that is R1 has to be decremented by the add instruction, that is by adding a negative value to this. Similarly, you can note that the chain of dependent instructions from load to the add and then add to the store determines the clock cycles count, which is equal to 6 in this particular case. Whereas for the unscheduled executions, it is equal to 10. Here in this example, one loop iteration and store back is completed in one array element every 6 clock cycles. But the actual work of operation on array elements take 3 clock cycles. That is only for the load, add, and store operations. The remaining 3 clock cycles per iteration are known as the loop overhead. And this loop overhead is there in order to evaluate the condition and stalls and the branch operations. That is, the loop overhead in this example is 100% because there are 6 cycles which are required, whereas in actual program without loop overhead, the cycles required are equal to 3. So this means that now we have to look into some technique to eliminate or reduce this loop overhead. The technique used for this purpose is known as the loop unrolling. Let us discuss this technique in detail. While talking about loop unrolling, we can say that in order to eliminate or reduce the impact of the loop overhead, in this particular example, we have said that it is equal to 3 clock cycles per loop. We have to get more operations within a loop, because if there are more operations within a loop, then the useful number of cycles will be more, whereas overhead will be again equal to 3 cycles. So this means that a simple way to increase this thing is that we should increase the number of instructions per loop. And this can be done by replicating the loop body for number of iterations and adjusting the loop termination code. This approach, which is usually referred to as the loop unrolling, we will discuss this with the help of our earlier example and re-executing this by using this loop unrolling technique. In order to discuss this technique in detail, let us assume that the register R1 is initially multiple of 32. This is because we are assuming that we want to have 4 iterations unrolled in one loop, and we know this thing, the R1 contains 8-byte double word value. Therefore, for 4 iterations, it must be having a value which should be multiple of 32. We also assume that the redundant computations are eliminated and the registers are not reused. So by making use of these assumptions, the unrolled loop will appear like this, where we are not assuming any scheduling so far. Here, the add instruction is merged into the load instruction of the second and third iteration codes, and branch not equal is dropped in the first 3 iterations. That is, the 3 branches and 3 decrement R1 operations are dropped over here. The R2 in the instruction branch not equal must now be set so that 32 R2 is the starting address. With this, let us have a look onto the execution of this program without scheduling. Note here that without scheduling, every operation in the unrolled loop is followed by dependent operations. For example, the load followed by the add has data dependence, Therefore, load has one stall. Similarly, two stalls are for add. One stall is for add immediate and one stall is for the branch. This loop is therefore executed in 28 clock cycles. Here these 28 clock cycles are such that 14 are for the instructions and 7 are for the stalls. This shows that this unrolled version is currently slower than the scheduled version which we discussed earlier, where one complete iteration takes only 6 cycles. So 4 iterations take 24 cycles, whereas in this case it is taking 28 cycles. Now let us discuss the performance of unrolled loop with scheduling. As you know that the instructions within a loop from different iterations can be reordered. Therefore, the loop unrolling can be used for scheduling. Here you can see that in this execution, where we are using loop unrolling as well as scheduling, the unrolled loop of the previous example is scheduled using the same latencies as we discussed earlier. Here, after unrolling, the load and add operations do not have any data dependence, so they are scheduled in sequence. Similarly, here the 4 load instructions for 4 iterations are executed in sequence in 4 clock cycles. Furthermore, you can see that the store instruction of the first iteration is issued in the 5th clock cycle without any stall. So it does not have dependence on the prior 3 load instructions. Furthermore, the branch condition evaluation instruction, which is add unsigned immediate, and we are adding a negative number, it is issued in the 11th clock cycle to avoid stall prior to the branch not equal, which is in fact issued in the 13th clock cycle. The store instruction of the 4th iteration is issued in the 14th clock cycle. Thus, it eliminates the stall after a branch. Note here that the execution time of unrolled loop has dropped to a total of 14 cycles, or in other words, we can say 14 divided by 4 iterations means 3.5 clock cycles per iteration or per element, as compared to the 7 cycles per iteration before scheduling the loop in this way. Our discussion so far reveals that the key to perform loop unrolling and scheduling is to know when and how the ordering among instructions be changed. Furthermore, to make the final decision, we must take into consideration the following points. Number 1, determine that it was legal to move store after the double word add unsigned immediate and branch not equal, and also find the amount to adjust the store offset. Number 2, determine that unrolling the loop would be useful by finding that the loop iterations were independent except for the loop maintenance code. Third, the use of different register to avoid unnecessary constraints that would be focused by using the same registers for different computations. We eliminate the extra test and branch instructions and adjust the loop termination and iteration code. The fifth thing that determine that the loads and stores in the unrolled loop can be interchanged by observing that the load and stores from the different iterations are independent. And finally, schedule the code, preserving any dependencies needed to yield the same result as the original code. So this shows that by taking care of these particular points, we can enhance the performance and we can reduce the number of stalls by scheduling as well as unrolling. From our discussion so far on to the loop unrolling and scheduling, we have observed that there are number of limits which are imposed onto the gains which we can achieve by this technique. These limits are, number one, the loop overhead. When we unrolled the loop, it generated sufficient parallelism among instructions that motivated the loop to be scheduled with no stalls. Now, the scheduling resulted in 14 clock cycles to issue all instructions with overhead of 2 cycles. Here, 1 cycle is for the instruction which maintains the index value. That is the instruction which is used to either subtract or increment the value by 8 so that the next loop location is determined. Whereas the second overhead is for the branch instruction which terminates the loop. That is, the overhead per iteration is equal to 2 by 4, because for the 4 iterations in one loop, there are 2 cycles. Therefore, for each iteration, the overhead is 1 by 2. Now, this overhead can be reduced if we increase the number of iterations. For example, if the number of iterations is increased to 8, the overhead remains 2 cycles. Therefore, the overhead per iteration will be reduced to 2 by 8, which is equal to 1 by 4. Similarly, if we go on increasing the number of instructions and the number of iterations within a loop, we can reduce the overhead in this particular case. However, we cannot increase the number of iterations beyond certain limits. The second limit, which can be discussed in details, is the growth in the code size. Here, we have to see that if we go on increasing the size of the code, then ultimately it will go on increasing the requirement for increasing the size of the cache block, which ultimately may result in the decrease in the cache miss rate. Similarly, the third limit can be the register pressure. The aggressive unrolling and scheduling of large code size may result in shortfall of registers, which is referred to as the register pressure. This is due to the fact that after aggressive scheduling of instruction, it may not be possible to allocate registers to live values. Therefore, while unrolling and scheduling, the compiler takes care of these limitations. Now, with this much discussion, on to the unrolling and scheduling, let us see how we can implement this loop unrolling and scheduling with the multiple issue in superscalars. Let us reconsider our previous example, but in this case, we consider 2 issues per cycle. In these 2 issues, one of the instructions may be an integer type instruction such as load, store, branch, or integer ALU. And the other instruction is the floating point instruction. Let us have a look onto this program, which is shown over here. Here, to schedule the loop without delay, it is unrolled 5 times. That is for 5-stage superscalar pipeline. We are unrolling this for 5 times in one particular loop. After unrolling the loop contains 5 load, add, and store instructions, and 1 each of the add, unsigned immediate, and branch not equal. Here you can see that the 2 issues take place in 3rd through 7th cycle, as the first load with next floating point ALU has a latency of 2. Similarly, the unrolled superscalar loop here runs whole of this program in 12 clock cycles. Therefore, it gives us clocks per iteration to be equal to 12 divided by 5, which is equal to 2.4. Now, this enhancement is against the earlier one, which was equal to 14 divided by 4, and that was resulting in a value of 3.5 for scheduled and unrolled on a simple 5-stage pipeline data path. Thus, it exhibits an improvement factor of 1.5 when we are using unrolling and scheduling in multiple issue pipeline architecture. So far, we have been talking about the static scheduling and loop unrolling. We have discussed a number of examples for loop unrolling without scheduling and loop unrolling with scheduling, and then loop unrolling with scheduling for multiple issues. Now I will discuss the static branch prediction. In the earlier lectures, while introducing the concepts of dynamic scheduling, we discussed dynamic branch predictors. The dynamic branch predictors predict the branch to be taken or not taken by considering the runtime behavior of the code. Here, we also introduced the concept of delayed branching, which is basically a static branch prediction technique. Delayed branches expose a pipeline hazard so that the compiler can reduce the penalty associated with the hazard. However, the static branch predictors are used in processors where the expectation is that the branch behavior is highly predictable at the compile time. Being able to accurately predict a branch at a compile time, it is also helpful for scheduling data hazards, for example, loop unrolling etc. Now, in order to discuss the static branch prediction, let us consider an example code segment, which is shown over here. Here, you can see that the dependencies of the subtract and branch equal to 0 on the load instruction. This shows that stall will be needed for the load instruction. Whereas, if it is predicted that the branch equals 0 was almost taken and that the value of R7 was not needed on the fall through path, then the speed of the program could be improved by moving the instruction, that is add unsigned R7, R8, R9 to the position after the load instruction. On the other hand, if it is predicted that the branch equals 0 was rarely taken and that the value of R4 was not needed on the taken path, then we could also consider moving the OR instruction after the load instruction. Furthermore, we can also use the information to better schedule any branch delay, as scheduling depends on knowing the branch behavior. Now let us see that how we can perform optimization in branch prediction. In order to perform optimization, we need to predict the branch statically when the program is compiled. There are several methods which we can use to statically predict the branch behavior. Let us discuss a few of these methods one by one. First of all, we can consider the simplest possible to predict branches as taken. Now, this scheme has an average misprediction rate that is equal to the untaken branch frequency, which is for spec 92, it is approximately equal to 34%. However, the misprediction rate ranges from 59% to 9%. 59% is for not very accurate and 9% is for accurate prediction. Second way is to predict on the basis of branch direction. Here, choosing the backward going branches to be taken and forward going branches to be not taken. And for spec programs, here we can see that more than 50% of the programs have got forward going branches, and the 50% or around 50% have got backward going branches. Hence, predicting all the branches taken is a better approach. This shows that we can derive the prediction accuracy of a predicted taken strategy and measure the accuracy of the profile scheme. For this purpose, let us have a look onto this graph, which shows the misprediction rate of spec 92 for a profile-based predictor. Here, you can see that the misprediction rate varies widely. It is generally better for the floating point programs as compared to the integer program. For floating point benchmarks, the misprediction rate varies from 4% to 9%, and for integer programs, it varies from 5% to 15%. Now, with this much discussion onto the static branch prediction, we can summarize our discussion today. Here, we have discussed three basic concepts in respect of static scheduling. Firstly, we talked about the basics of static scheduling. Then we discussed in detail the unrolling technique, where the unrolling technique can be used either with a simple MIPS 5-stage pipeline, where it gives relatively better performance, but when we include scheduling in this, the performance is enhanced by 1.5 times. Whereas when the scheduling as well as unrolling is used for a superscalar for multiple issue case, then the performance is further enhanced. So with this much discussion on to the static prediction, today we will have a stop over here, and next time I will be discussing in details the static scheduling in very large instruction word processors. We will also be taking up some practical examples, and we will analyze the performance of different types of scheduling techniques. So with this much discussions today, I say you Allah Hafiz. Thank you very much.